outside. Make sure that they be careful when driving this thing. Good morning. Thank you for being here. Today, it's a pleasure for me to introduce Stuart. He's sort of an emeritus professor at GNS in New Zealand. He was visiting Spain, so I knew it, and I twisted his hand to give this talk here. He's going to present some real new data. Well, perhaps not that new, but it's real big data set on controlled seismic shores in New Zealand. Basically, he is based in Wellington. He's been working in almost everywhere in New Zealand and then in the Ross Sea. He's been involved in the OCDP, so he's actually been part of the game on deep seismics, especially on marine. And mostly he's been working in control source methods, provide detailed images of the Earth crust, and integrate these with a number of different data sets from satellite, gravity, magnetics, and MT. So after saying that, I think, Stuart, the floor is yours.
Okay. Thank you very much, Ramon. So I hope the people online can hear me okay, which is good. And I'm just going to talk today about the crustal structure that is an evolving story to understand the Hikurangi margin. So this is a subducting margin that goes through New Zealand. And these are some of my co-authors. Some of these are people that have been involved in the New Zealand geophysics scene for a long time. And some of them involve international partners and sometimes going back 20, 30 years. So the key players here are Dan Bassett and Brooke Tozer, and they've done a lot of the kind of heavy lifting for this project. Right, let's see. Okay, the Hikurangi margin. So this is the plate boundary that goes through the North Island in New Zealand. It's part of the plate tectonic setting for the whole planet. And in New Zealand, we have the Australian plate subducting beneath the North Island of New Zealand. So if this works, this is the Australian plate. It's subducting 4.3 centimeters per year beneath the North Island. So the subducting margin trough is this dashed line. The Australian plate here is thickened, Hikurangi Plateau. It's a thickened oceanic crust. The North Island is, because this is thickened crust, the North Island and the accretionary prism, a lot of it is exposed. So we know a lot about the subducting margin here from permanent network of GPS, GNSS receivers onshore, and we have a seismic network of over 100 seismographs along this part of the margin. So this shows you here information about the subducting margin. From GPS, we know the plate in the Wellington region where I live is locked. That's the red patch. The coupling coefficient is high. In the northern part of the margin, it is slipping and sliding, and it's extending and opening in the Taupo volcanic zone. So locked, unlocked. The transition is this boundary through here, and it's marked by a couple of features. We also get slow slip. So these are earthquakes, but you don't feel them. So the GPS records slow earth motion to the east, and it's very shallow in the north, and it's very deep in the south. So these occur very regularly, these slow slip seismic events, every 2 to 3 years. These deeper ones are larger and occur every 6 to 7 years. And there's some that are more intermittent in this region here. So these are the components. In the central part here, weak coupling, shallow frequency, SSEs, slow slip events. In the south, strong coupling, deep SSEs, and upper plate compression. So the science question that we want to address here is, to what extent does crustal structure and architecture contribute to the differences from south to north that kind of control part of the slip behavior on the margin? So that was the overriding question, but I'm going to see if I can manage this. Jump out, show this movie. This is a simulation of the Kaikoura earthquake, which occurred in 2016. It was a magnitude 7.8, and this is another motivation for this study. So this is not data. This is a simulation, Ramon. So this is spectrum 3D. The input into this model for the Kaikoura event is made up of physical properties of the crust, and so our work contributes to the model, the underpinning model for earthquake simulations like this. So the reason that we do our kind of tomography, our work, is to feed into this hazard mitigation risk study. So this earthquake did quite a lot of damage in Wellington, and you can see that the rupture terminated, fortunately, in Cook Strait. But those waves, as they propagate, you can see that the yellows are where there's more shaking. So part of our study is to collect this 3D velocity information, and that informs how much ground shaking is occurring in these events. So not only the path of the propagation, but also the response of the Earth. So I'm going to stop it there because it goes on. Okay, so we've been doing this work for a long time, and the components that go into our tomography are travel times from both from active source, and we also starting to use passive source. So if I can just show this. Yeah, so we use air guns offshore. We have receivers onshore and receivers at the bottom of the ocean. And then onshore, we have explosions. We've done surveys where we've had large explosions and recorded the wave propagation with seismographs on the surface. And as I said, we're now utilizing earthquakes as well. So we started this work in 1994, pretty much. We've curated the data set all the way up to the present. Even though this data set is old, we still have all of the data recovered on receivers and backed up on computers. And we use this very old Italian ship that's now been decommissioned for this survey in 1994. So I'm just going to run through some of the other surveys. In 2001, we had a transect through the North Island of New Zealand. Night survey offshore, a whole lot of receivers onshore. And we did it in two parts. We had the ship offshore, and then the following year, we had explosions onshore. So these surveys pretty much follow the same kind of sequence. We utilized a commercial vessel that was collecting seismic data along the margin, and then put out some receivers for this. This is the permanent network of seismographs, broadband, and then we have some short period as well. So we put out these short periods to capitalize on that survey. And then in 2009 and 11, we collected a larger data set together with the United States, where we had more explosions, more onshore, offshore OBSs. We capitalized on a survey that the Crown was collecting for oil exploration. We don't do that anymore, unfortunately. But we utilized all of the airgun sources into the array that we had onshore. And we also had these explosions. So this is a big survey, cost a lot of money. We don't have the resources to do this stuff anymore. It was fun. It was good. And now we collected data from an academic survey. These are the red lines, collected in 2018. This was a Shire survey with the US. Plus, an oil company collected data in 2014. So those are the kind of grey lines underneath. And so we now have, at this stage, when we publish this paper, we have all the required constraints to do the 3D regional model of the Hikurangi Subduction Zone. So this just shows the quality of the data that we have. So the top panel is just one of these stations onshore and shows you the collection of traces, air guns. Every one of these is an air gun pop. And we can see crustal arrivals from the forearc, crustal arrivals from the subducting crust, and PN arrivals from the subducting mantle. So the data quality is super good. We also have on a lot of these gathers crustal SG phases, which we are now thinking about using. So every one of these stations, it collected all of the onshore, offshore data sets, and I'll show you a map in a minute. So along strike, this is B, we also collected really good data, PG in the forearcs, subducting mantle, and excellent arrivals. So we've collected up all these arrivals, and this is what we use in the 3D tomography. So here's another station just to show you that we can do the stuff all up and down the coast, both in the north and the south, the same sort of thing, PG arrivals, and we have really good offsets, and I'll show you a histogram of the offsets to show you how constrained the model is. So this is the OBS data, excellent OBS data from the Shire survey. This is one of the OBSs here, and another OBS into the south. So both across the margin which is creeping and the margin which is locked. So really good phases. And as well as that PMP, we've also started to think about using PMP reflection arrivals in our tomography. Currently, what I show you does not use PMP or the shear waves. So it's just a P-wave velocity model. Right, okay, so this is a summary of the data set that we have used in our tomography to date. We got 167 seismic lines of usable data. It's a lot of receiver gathers and a lot of picks, and the offset range is from 12 to about just a bit over 384 kilometers. The ocean bottom data is more limited. We only have 7 lines, 95 deployments, about 1/3 of a million picks, and our offsets are a bit less than 100 kilometers. So that histogram down there shows you the offset. So really, really good coverage out to about 150 kilometer offsets. Good. So here's the tomographic conversion setup. We had 1,000 kilometers by 480 kilometers by 55 kilometer velocity model. So we do this tomography using a supercomputer. It takes a bit of time. 2 kilometer horizontal node increments, 500 meters. So over 13.3 million model parameters. And we're using Harm Van Avondok's code. And we do the shortest path method and then inversion, Starting velocity model is we use the earthquake velocity model from Donna Eberhard Phillips because it provides a 3D model to start with from earthquake tomography. We use stacking velocities. This is one of the stacking velocities from one of the seismic lines. So that we use those as a constraint. And we have a number of those lines that we've used. And we've also got 6 2D wide angle OBS lines. And we build that into the initial velocity model. So this is the initial model, starting model. The RMS met fit is not very good. Chi-squared is not that greatest, but the final velocity model is much better. So this is just one of the transects through our 3D velocity model. So the next slide is a bit of a movie to show you 3D tomography model as we've calculated it. First, before I do that, is the resolution. Resolution is really good, up to about 25 kilometers depth, and is well resolved pretty much along the whole margin. Towards the west, not so good, and then offshore beyond the subduction zone, also not that great. So, and these are along strike. So south to north of the margin, and then this is down dip of the margin, east to west. So pretty well resolved, better than the earthquake tomography, but I'll show you later, we're actually trying to improve that a bit more. We've found some more data. Hopefully this might run. So this is the model, the 3D model going from south to north, and there's a few features. I'll run it a couple of times. So the width of the accretionary prism and the sedimentary section, you'll see that variable along the margin, location of the crustal backstop, which is where the velocity transitions from the blues into the yellows and greens. The velocity structure of the forearc crust is changing, and the geometry of the Hikurangi Plateau also is subduction, and the mantle velocities. So just we'll run that again. There's a lot taken from south to north. Oops, it's high velocity in the crust to space. So one of the really interesting features you'll see as we go to the north, you'll see the velocity in the here beneath the crust is quite low, really low. This was the region that in the Kaikoura earthquake, the movie didn't run far enough, but during the Kaikoura earthquake, there was a lot of ground shaking in the Gisborne region, so that's up here. So that sedimentary basin in the Gisborne region, I'll show you in a minute, is really thick, and it really resonated during the earthquake. Oops. Okay, so this is some stills of the movie. So the crustal rocks extend to within 25 to 30 kilometers of the deformation front in the south. Where are we? This is to this. I think this is south. Yeah, F. Yeah, in the south to the north. So this is the basin I was describing before, offshore Gisborne. So the outer which widens in the central part of the margin. Northern Hikurangi maintains this incredibly low wave speed, much higher and much deeper than in the south. And low wave speeds offshore is consistent, as I said, with the observation of ground shaking here. So there's quite a lot of variation. These arrows, this is the Hikurangi trough, the subducting margin. This is kind of the edge of the continental shelf, the red arrows, and that's the land to sea transition across there. So really interesting. This is now the other direction along strike. And we can see that the crustal thickness of the Hikurangi Plateau thins from south to north. So yeah, this is the south, this is the north. The crust of the plateau thins. And there's a few other features as you go inward. So south to north is a reduction in the mantle seismic velocities, and south to north is a reduction in the upper plate wave speeds. This is just pretty much along the coastline. I just want to show this one. So sharp. So as beneath that, this is where the resolution is really good. You can see sharp along strike changes in the upper plate wave speed. So here, here, and here, and I think I've marked those. Yep. So this tomography is identified these boundaries, and I'll talk a little bit more about those boundaries now for the next little while, and we can discuss those, how they impact the seismic slip behavior on the margin. Okay, so we collected, as well as the velocity model, we've collected a lot of seismic reflection data, and we're using that to inform some of this interpretation. So this is a busy slide. So this is the Shire data we collected in 2018, the MCS data. Also reveals some interesting features to the south and to the north. So what I show here is just this segment, that's that seismic line here, and then across the transition, this is this locked to unlocked transition. This is seismic line here. So to the south, we have a really reflective crust. This is a subducting interface, and we have this kind of really strong upper plate reflector, which we think is either the backstop to the margin, and it's probably a geological terrain. So the geological terrains are mapped here. And you can see there's a kind of stepping of the terrains back into the ranges to the north. So that in contrast to the north of the margin, we just have a more transparent upper plate. So we don't see that mid-crustal reflector, which we think is a terrain boundary. Right, and this terrain boundary corresponds to a wave speed of about 4.5 kilometers. Okay, we've tracked the mapping of this. We show a map here of the depth to that 4.5 kilometers per section, per second. And I put on some of the features. So those are the kind of, if I just go back, see if that works. Yeah. So I'll put on some of the features that we observed previously. This refers to 1, 2, and 3. So we get the strong agreement in the south between the geological basement outcrops and where the high wave speeds are maintained near the surface. And we suggest this upper plate velocity structure reflects part of the geological architecture of the margin. The map also reveals these abrupt changes, these 1, 2, and 3, which we mark as northern Raucuma Peninsula, that's that one. This kind of region in here, south of Gisborne, and in the Cook Strait region. All right, so this is part of our interpretation of what those features are, and we've taken a tectonic evolution of New Zealand. So one of my colleagues, Hanu Seabrook, has constructed a G-plates model that goes back 20 million years. So these are the features that we observe: the Raucuma Peninsula one, the south of Gisborne, and the Cook Strait. All right, so 26 million years, New Zealand was barely recognizable. This is the Chatham Rise and the Hikurangi Plateau that is now subducting beneath the margin. So basically, the pole of rotation is way to the south. New Zealand has to basically fold back towards Australia, and we have all of this oceanic crust which is now subducted. So I'll just run this forward, and you can see that the subducting margin initiates along here, and part of the rotation is taken up in this Veni minus fracture zones. You rotate that even further and right up to the middle. So we can see that this rollback is we infer that this number 1 is part of the Veni minus fracture zone. The Pacific plate rollback that is rotating around the Gisborne region is the structure in 2, and taken up the structure, most recent structure, is the bend in the Marlborough Cook Strait region is number 3. So that's part of that. I'll just go back so you can see those again. So 26 million years, 20 million years, 11, 6, 4, 2, 0. New Zealand's pretty complicated. Okay. Right, so this is the depth to basement. And I'm just reinforcing some of the points we made earlier, that the rotation boundary accommodated east-west rotation of the Raukuma Peninsula, and number 3 is this ancestral alpine fault, which has taken up most of the plate rotation in the last 4 or 5 million years. So the velocity structure informs the geological evolution of this part of the margin, and from which we can kind of infer some of the slip behavior that we're seeing. So the crustal backstop that I referred to, this was the upper crustal reflector that you could see to the south. The MCS data show that it's 4.5 kilometers. So we've used this threshold to make some observations of the margin. So we can say that the position of the backstop influences this updip transition from locking in the south to unlocking in the north. And the position of this updip transition is variable and may be a key control on sedimentogenesis. So the SSE distribution, position of the backstop also may influence the updip position of SSEs. Oops. Whoa. I'm running ahead of myself. Right, yeah. So in this unlocking region, where we don't have this upper crustal reflector and where the terrains are further back, then this is influencing, we think this is influencing the distribution of the shallow slow slip. And then in the deeper part, where the terrain boundary is much shallower, that's influencing these deeper SSEs. These deeper SSEs we find is at the intersection of where the subducting plate of the Pacific plate is intersecting the Australian plate. And the position of the margin is quite a lot wider in the south and narrower in the north. So a key summary of the observations that we've made is that the regional integration of all of the active and passive seismic data overcomes the limitations of these 2D surveys that we're used to doing, where they are high resolution along a profile, but low spatial resolution away from the profile. And the earthquake tomography, on the other hand, is high spatial extent, but very low resolution. So our work using the onshore offshore has overcome some of these limitations. The seismic velocities in the overlying thrust plate predominantly kind of reflect geological architecture, and the position of the backstop that is really controlling the slip behavior, we contend, it shows a lot of differences in the frictional transitions and the width of the subduction zone. So what are we going to do next? We're starting to relocate earthquakes into our 3D velocity model and then updating the velocity model using the earthquakes. We're starting to pick the S arrivals, and which is quite difficult, and we're using some machine learning, but also some guidance. Now that we have a velocity, P-wave velocity model, we can simulate the shear wave velocity picks, and we can use that to guide our shear wave velocity picking. And then once we have VP and VS, we can also do density. We're analyzing the wide angle reflections, the PM phases from the reflections, and we'll use those also in our tomography. Lastly, one of the data sets that we've recently got our hands on is a 3D data set that Schlumberger collected in 2017. So this survey has over 1 million shots in it. And this is going to require a lot of guidance and machine learning and the picking, because every one of these onshore seismic stations will have we think, we've looked at the data and most of the data is pretty good quality, they would have recorded these million picks. So there's an awful lot of more work beyond just humans to be able to pick all of this stuff. In addition, we collected in 2018 an academic 3D survey. This was 60 kilometers by 15 kilometers. The Schlumberger survey was much bigger, but we will start to look at anisotropy data, see whether there's anisotropy velocity models that we can incorporate into our 3D tomography. In addition to that, because the 3D survey from the Schlumberger and the NZ3D survey are co-located with previous seismic lines, and that's what I show here, then we probably may be able to, in inverted commas, look at 4D changes in the reflections of PMP to see whether there's, after each slow slip event or the Kaikoura earthquake, there may be changes in the physical properties. So this is a project that we may yet attempt. So thank you for your attention. I'm quite happy to answer any questions and go back over anything that I skipped. Yeah. Thanks.
Thank you for the very impressive data set. I guess it's a fruit of a number of years of work.
Yeah.
So any questions from the floor?
Thank you for your talk, Stuart. Thank you. I would like to know, I know very little or zero about the geology of the New Zealand islands. Can you explain a little bit the geology onshore, please?
Yeah.
I think that you didn't show any map, but maybe with the...
Yeah. Maybe I'll just go back to
see if there is any big difference in between the Northern Island and the Southern Island and a kind of transverse fault in between.
Yeah. Okay. Right. Okay. So because the plate boundary runs as a subduction zone through New Zealand, so here the Pacific plate is subducting beneath the Australian plate. Here they're sliding past each other. So the Pacific plate is sliding past the Australian plate. And then in the south of the South Island, Pusica, the Australian plate is diving down beneath the Pacific plate. So most of the margin that I was talking about is accretionary, because this is thick oceanic crust. That accretionary margin that's mostly Miocene and younger is exposed. You can see lots of active faulting. In the ranges behind that, that's the kind of backstop, is made up of older Jurassic sediments that underlie all of basically part of the margin. So those basement terrains that I refer to down here are older Cretaceous rocks, and some of them outcrop at the coast just sporadically. And then in behind that is sedimentary basins and the Taupo volcanic zone, which is active, less than 2 million years volcanic crust. Out further to the west, this is sedimentary basin. This is where the oil and gas fields were located, still are located here. There's an active volcano here, an active volcano through here. Then there's this Miocene volcanic arc, so that's part of that rollback into the present day. And then there's even older arc crust and ocean floor that's abducted onto the North Island. So yes, quite complicated. There's a marked boundary through here that is a serpentinized mantle that's been exhumed, and that really is an older pre-Cretaceous tectonic part of the Australian Gondwana margin. So yeah, most of the geology, part of the deformation in terms of the plate boundary rollback is incorporated into Marlborough and then into Raukumara. This margin here is compressional, so there's a vector that generates the Southern Alps. This margin is rotating, so that most of the margin you can see is faster in the north and less in the south, and becomes more oblique. So these arrows become, and then you can see that it strikes slip through here with a component of compression. What else can I say? Yeah, all of the faults along here are pretty active. And they often involve prior faults, so they're reactivating older faults. Yeah.
Okay,
Does
thank you
that
very
help?
much. So it's a kind of continental block.
Yeah. So this is continental. This is continental collision. This is oceanic crust continental collision. Yeah. And normally you could see this accretionary prism if you look at other subduction zones, many, Oregon, Alaska, Japan. Most of this is offshore, but you can walk along the coast. You can walk along here and see folds and thrusting. Yeah.
Any other question?
Yep.
How thick is that plateau? Oceanic plateau.
The oceanic plateau, yeah, I show some slides. It's about 10 to 12 kilometers. So it's thicker in the south and then thinner in the north. It's not a lot of difference. So about 12 kilometers to about 10 kilometers. Yeah.
So like compared to the Anjang
Yeah.
Java plateau is very thin.
It's thinner. Yeah. Yeah. There is a story here with the Hikurangi Plateau. It was combined probably with the Manahiki Plateau. So the Manahiki Plateau has these segments which are thinner and thicker. Also, so this Hikurangi Plateau was probably part of that. Then the Manahiki Plateau was part of the Onton Java bigger sequence, and it's fragmented a long time ago.
So is that why you think you can continue to roll back the subduction zones, because that oceanic plateau is not very thick? And if you look at the Anjang Java plateau, there's really no rollback going on there now. Solomon Islands, Vanuatu, around there. Yeah.
Yeah. Yes. So because it's not as thick, it has resisted subduction. So the transition from Hikurangi Plateau to normal oceanic crust is just to the north of New Zealand. So as that thickened crust trying to subduct is kind of wedged into this fragment of continent, which is Chatham Rise. So as that's indented, then the margin, the subducting margin, is rolled back. And this is trying to subduct. That contributes to the complexity. Yeah.
It's curious, the setting, because it's the same as the southern termination of the Ryukyu subduction zone.
Yes.
Just not as bent.
Yeah. Yeah.
Into the Philippine Sea Plate.
That's correct. So there is a paper in geology that one of the co-authors, Laura Wallace, has compared Hikurangi to Ryukyu. So there, let me get this right. So it's the Shikoku area that is locked, and it's the Kyushu area that's unlocked. So it's a kind of, it's a mirror image of this. Yeah. Yeah. And their volcanic arc is through Kyushu, through that southern island, yeah, with that opening of Kumamoto, and so that's the equivalent of the TVZ.
Any other question? I had. Okay.
Thank you. Following your conclusions and future work you show us, I was wondering if there are any correlation with the GPS network in order to explore the different grades of coupling along the subduction zone, or for example, to explore the occurrence of slow earthquakes. That I know it's something
Yeah.
they are exploring there.
Yeah, so the GPS network is continuous, so it's a really high resolution. So the map I showed. So this coupling map is derived from the inversion of the GPS data. And so in that, you know, Charles and Laura, so what they do is they don't include the slow slip events in their construction of the locking. So this is a long-term, nearly a decade now of continuous GPS measurements. And it reflects the fact that this part of Wellington and Wairarapa is not moving. So in the GPS signals, you don't see any signal of eastward motion, as opposed to Gisborne, stations up in here, that shows a continuous horizontal motion to the east. And so we know that we know that this area is moving to the east and this area is locked. However, so punctuating that whole continuous record is these slow slip events. So every now and again, we get a slow slip event, it moves to the east and then drops in a slow slip event and then accumulates to the east again and then drops. This region does not see that, but back here and behind the Kapiti coast, we see every 7 or 6 years, we see a big event, and in Manawatu. So yeah, quite interesting, really interesting. And as I said, we think we have some constraining reason why it's locked here in terms of its crustal architecture. The big, I guess what I didn't say, the scary part is that if this moves in an earthquake, this whole region moves in a big earthquake, which we anticipate, then that would be a magnitude 8 earthquake. And that's the scary thing. And it's kind of underpinning all of the motivation for these studies. Yeah.
Wellington.
Yeah.
Thank you.
Okay. Yeah.
Is a active volcanic zone? There is active volcanism?
Yes.
Okay.
Yes. So so that red dashed line basically outlines all of the active volcanoes. So there's active volcanoes here. This triangle is Whakaari White Island that erupted a few years ago, killing quite a few people. And GNS has monitored this station, has monitored this island. We have not returned to that island since the eruption because it's still too dangerous. Yeah. So yeah, lots of active geothermal fields, high temperature, boiling. So incredibly interesting, and lots of active faults through here.
What's the distance more or less from the red dot line to the black dot line?
So that distance is about 300 kilometers. Yeah.
And from the red to the offshore?
Oh, the width of that is about 100.
I mean, the subduction zone.
Oh, right out to the subduction zone.
Yeah.
That's over 200 kilometers. Yeah.
Hi, actually, you started to answer my question anyway, but I was just wondering, with all these studies, if you are gaining insights into when the next huge subduction earthquake might happen.
Yeah. So the work I do doesn't directly inform that, but I have colleagues. I haven't included here, I could have, but so my colleagues who look at paleoseismic records down the coast, this is really hard work because they look at, for example, in behind this peninsula, Mahia Peninsula, there's a number of lagoons, and they core into the lagoons, and down here in Marlborough, there's more lagoons. They collect a record of the most recent earthquakes and tsunamis. So if there is a tsunami because it's a subduction zone event, then they correlate in time the same event that occurs up in here with an event down here. And so they can say, well, that whole part of the margin moved in an earthquake. We know that's roughly every 1,000 years. We can see other areas where we can correlate over shorter distances. For example, we know this region is subject to more tsunami earthquakes. There were 2 tsunami earthquakes in 1942 in the offshore Gisborne region, probably related to a seamount subducting. So they occur, tsunamigenic earthquakes in the region up here occur more frequently and less frequently down here. So the implication of this region, it's prone to bigger events, but less often. And so that's the work of Kate Clark. There's a good publication that she has. I can give it to Ramon, that looked at historical record along the margin. And so the big difficulty they have is correlating in time the diatoms and dinoflagellates from tsunamis into freshwater lagoons versus cyclones, which occur also regularly along these part of the coast. And so plus trying to understand whether these upper plate faults also rupture in big events. So how to differentiate upper plate, cyclones, megathrust earthquakes is quite difficult. Yeah, it's ongoing. But yeah, we're attempting to do that. Yeah.
Thank you.
Any other thoughts? I had a question. When you showed the Boston model, the southern part, if you could show that, it struck my eye that there's a high, I think it's a high velocity anomaly in the middle, where you had the cross section. This one. Yeah, right there.
Oh yeah.
That's red dot
yeah.
over there.
Yeah,
What the
yeah.
hell is doing there?
What is that guy?
The very south.
Yeah.
That red spot.
So this is F.
That's it. Yeah. This has to do with the locking or?
No. So that red spot. Okay, so that's the coast, and then there's a bit of land, and then we're off onto the Whanganui Basin. So what is not showing here is in this basin, which is a large sedimentary basin, there are a number of very large thrust faults. So those thrust faults, so if I was to, you can see here the mantle reflector of the Australian plate, and you can see the subducting Pacific plate. So there are thrust faults which originate from that point back into the Taranaki Graben, Taranaki region. And so it looks like this is kind of, it looks to be a block of older rock that is separated by thrust faults. But it's a very good question, and it's something that we will try and identify and resolve with the more data. So we haven't, so in addition to all of the data that we've had, we've also, there's some 3D seismic data in Whanganui Basin and offshore Taranaki, which we will incorporate into the next version of the model.
And a curiosity question, how long does the inversion takes?
Oh yeah, okay. So it takes, so yes, it takes a few weeks. Yeah.
Few weeks.
It takes a few weeks, and if we add, like we're getting now, So to update our velocity models, like for example, so that everything here has been published in a paper in JGR. One of the reviewers, could be in this room, asked us to do a Monte Carlo, and it would take us months. But, you know, basically you do the inversion and you perturb the model and you run it again. And we just wrote a note to say no. Because the inversion takes so long, we would just never publish it. So we, as we incorporate more and more data, and once we incorporate the Schlumberger data, there's just no way we can, it's going to take, we're going to have to find more efficiency in the system. Yeah.
So the travel time picking, I guess it was also done automatic travel time
No,
picking,
no.
because otherwise.
All of the travel time picking for this paper that's in JGR, we did manually.
Manually.
Yeah. So, okay, it's not as bad as you imagine. We used an interpretation system like Keenan Suite. We used Sizeware. So basically, you dump all of the SegWire gathers in as seismic lines into the interpretation system, and then each kind of line that I showed in that map, well, we can pick at the intersections and get them all correct, and that sets the guidelines for the next one, and it's actually pretty tedious. Dan has done most of that, but we realized that once we've got these new data sets, there's no way. He just refuses to do any more. So we're going to have to be smarter. Yeah.
Thank you very much, Stuart.
Yeah.
Any other thoughts? Last. Well, if there's no, I would like to thank you personally on this talk. Amazing data set. Thank you very much for coming here.